Yes, so welcome everyone again. In today's webinar, I want to talk again about a topic around StableNet and AIOps, showing different possibilities, how automation can be further conducted by adding data science approaches and machine learning approaches. And to that end, today, I want to focus on some log analysis. In the previous webinars, some of you might have seen already that we had been looking into time series analysis, also with Jupyter notebooks with interactive Python, and into topology analysis. And today we want to circle more around text-based analysis. And as an example for texts that we want to analyze, we look into log messages. We could also think about, for instance, analyzing configuration files in a similar way. But for the sake of having a nice example here, we chose log messages. So I'm directly starting here in the interactive Jupyter notebook. As always, this means that I have some cells that contain code and some cells that just contain additional information. So if someone is later on receiving this notebook and wants to work with it on his own or on her own, he or she can just refer to the text as well. So if we look at the first cell here, this is just like the standards, importing different libraries, which basically shows us that there is a lot of standard stuff that we can use in terms of Python modules that we can just import. And we have a tiny little part down here where we are actually adding some extra stuff that we can provide together with the notebook, and that we just basically put separately in different files for the sake of having the notebook not be too long. So there's the topology package that we basically have been using already for the topology analysis to display weather maps, for instance. There is a text analysis package which bundles some of the stuff that is specifically for this log analysis today. And there is the StableNet utility package, which we use just to connect to the REST API of StableNet in a convenient way. So I'm just re-executing that cell. It was executed already, but I'm just re-executing it here. The same for this cell. This is basically just a standard that by now you should have seen me using many times. This is just like contacting a StableNet server and getting connected. So the username is provided here and the password I will just add here in the console. Now, once this is done, I'm actually receiving the log messages from the server. In order to do that, I'm here in the Python code. I'm actually just calling a one-line command, load log data, which has separate parameters. In the backend, this is actually using the REST API call for getting events logs. But this is not something that you need to take care of here. We bundle this for you in a method, and you can just use the parameters for the number of logs, the start time, and the end time. And this will actually, starting from the provided start time until the provided end time, this will provide you all the logs, but you can equally limit it to a maximum number. So I'm just calling this. By the way, we also integrated a functionality, as you can see here, where you can read it from a file instead. So this is just for debugging purposes. If you download the file, the log files you can also store them locally. As you can see here, in the time frame from a month ago until today, until noon, I have only 73,000 log messages in my demo system. So I provided a number of maximum 200,000, but obviously I can get only as many as I actually have. So here is the head of the messages. So you see the first 5 messages. And you can see that all of these messages have a device ID, a syslog priority, a syslog time, and a message. And now we actually start looking into this a bit more in detail. First of all, we are getting rid here of some irrelevant information, removing, among others, punctuation marks, digits, stop words, the IP address, or the username. In this case, this is just to make this look more similar to each other in order to allow more detailed analysis. And here we have just an arbitrary example, like the first message. It previously looked this way and afterwards looked that way. So some information has been removed. But now maybe let's get into some more visual examples quite quickly to keep this webinar short. So the first thing I'm doing here is looking again at the number of entries and also getting the unique list of devices that is contained in these log messages and getting a number of devices then and just printing this out. So I will rerun that code. That goes fast here in this case. And I can see again, as seen before, that I have around 73,000 log entries from 14 different devices. And now that's where it becomes more interesting. Let's now take this and plot a word cloud. So this is recalculating here, so it takes a moment. And actually here I'm now getting one of these tag clouds that most of you might probably know from other usages, where you can actually see an indication of how frequent certain words are contained in these log messages. Obviously, with the set here in a demo system, this looks differently as it might look, or it probably does look in a customer network, but we can see here some indicators of what are the words that are frequent in our test set here. And this is as easy as changing to another server, so obviously we can run the same on other messages. Now let's continue here. Another thing we might want to look at is actually getting for the priority of for the severity of the syslog messages, and now actually getting a pie chart on how they are distributed. So I'm rerunning this again. And here you can see that all the messages we have, like a bit more than half of it is a syslog priority of 6, which is a low priority. The higher, the lower. There is also, like, it's almost 75% is 6 or 7. And then there is the last quarter is 4 or higher. And you can see this here in a pie chart. And now we are getting to the next step where we are actually grouping this by device ID, sorting it and showing the counts. So this gives us here a bar chart where we actually have for each device ID, we have the total number of syslogs in a stacked way, colored by syslog priority. And this also gives you an indication here that there seems to be one set of devices which has these level 7 syslog priorities and a lot of level 6 priorities. And there is a second set of devices which is rather, which is basically not containing any level 7 priorities, but containing higher priorities here. Maybe now, as a next step, let's see, we don't just want to look at the total number of messages that has been coming from the devices in the last month, because I had set up a range of 1 month. But now we actually want to have this over time. So we are creating a scatter plot. I'm just rerunning this here. And what we are basically doing here, using the same color spectrum, we are now scattering this over time. So on the x-axis, we have the time now since the last month. So you actually see that apparently I don't have any messages from before beginning of July, because we just set this up, this demo system specifically for that webinar. So even if I requested the end of June, I'm just getting the earliest messages from beginning of July. And what you can also see here is you have on the x-axis, you have the time, on the y-axis, you have the priority, and you actually have a plot that indicates of which priority, when did I receive log messages. So this is a good indicator to see if there is a certain pattern or if there is a certain cluster of certain priorities in a certain time frame. Now, based on this, I think the next thing that could be interesting is knowing actually not just when log messages arrive, but also getting an understanding of how many log messages arrived at that particular point. And obviously, if we have a two-dimensional plot here, we can't actually see the number of messages at this certain point. There might be hundreds of messages resulting in a single dot. So for this, we are now creating a histogram. Statistically for the different syslog priorities and looking at the density of each of these ticks on how many messages have been there. And we are plotting this now in a three-dimensional histogram. So I'm just rerunning this. And there we go. We get a similar plot as the one above here. But now we actually have, in addition to the time and the priority, which basically resembles the plot from before, we have a third dimension, which is actually indicating the number of messages. So now we can suddenly see that first of all, there are, again, we can see that there are many more level 6 messages than level 2, for instance. We can also see that level 6 seems to have some continuous spikes at certain points. We can also see that there is one point in time where there have been many more messages as anywhere else. So this is just showing you more possibilities, how basically, for those of you who are a bit more familiar with Python, you will see that most of this is just like laying out the graph, like setting labels, setting titles, like just some small for loop here, actually calculating this. So it's not very complex, but you can achieve a lot of stuff with the out-of-the-box functionality. Now, let's maybe for the next part here, let's move a little bit closer towards StableNet, because so far we have just worked with a list of log messages that contain device IDs, priorities, timestamps, and messages, but we have not yet made use of the fact that StableNet is actually offering us additional information. So to that end, now we will actually get topology information from StableNet, and we will also get tag information from StableNet, because obviously this is one of the real benefits of StableNet, that you can use tags to add additional metadata to your devices and your taggables. So let's run this again. I'm just now using another command to get device names and tags for the log messages. And if you actually look at this table now, you will see that the front part is the same as before, but now I'm also resolving the device IDs and device names to know which device this is. And I'm also adding another column here which contains all the tags of that device. So this gives me a possibility to get a better understanding and a better analysis. So now let's look at the neighborhood graph. So what I'm doing here is I'm using my topology analysis methods that I had in the previous webinar, and I'm actually plotting a neighborhood graph for all devices that are contained in the log. And what I can actually see here, if I'm looking at this picture, I can see that all the devices that are colored and that contain a digit number here are indicating that what is the highest priority of this of any log message on that device. So in this case, it's priority 1, priority 3, priority 2, and the size of the node also indicates on how many messages have been there. So you can see I have a factor to influence that. I can make this a bit more extreme. If I put a 5,000 here, it's a bit more extreme to differentiate. I can even put a 10,000 maybe. So this is just to indicate on how many messages have been on which node. And the gray nodes, as the not a number indicates, don't have any node log messages in my system. So this is another possibility to analyze if there's potentially, if there are joint logs on neighbor devices, or if this is on a completely different spot of the network. So now moving forward a bit, I'm now limiting the maximum priority of the log messages I look at, and I'm only filtering to messages that have a priority of 2 or 1. Okay, this is calculated. And if I'm now plotting this graph again with this limited set, the alert DF, which is just priority 1 and 2, you would actually expect this to be 2 parts of a network, because the nodes with the 3 drop out. And if I'm running this, this is actually what happens. So I'm having one neighborhood graph here with nodes that have priority 2, and one neighborhood graph with nodes that have priority level 1 in terms of syslogs. Another thing we can do now, getting back to the tags, is now we actually don't want to look at the messages itself, but we want to look now at the tags and find out if there are any common tags across the different syslog messages that we have. And here we are looking again at our alert set. So we are just looking at those devices that have messages with priority 1 and 2. And here we can actually see that there seems to be some higher frequency for words like VLAB, Infosim, headquarters, Cisco. And this is actually, for those who have some background information, we actually know that those are our Cisco devices in the VLAB. So this is helping me again finding out some more similarities. And now towards the end of my webinar, to keep more or less in that 15 minutes time frame, I want to look into something even more complex. So what we did here in the following is we took two different approaches that we also linked here in the text parts, and that you can have a read on if you are interested in more details. We used two approaches to do log anomaly detection, so to find specific messages that somewhat stand out of the rest of the messages. The first approach is based on principal component analysis. So what we are basically doing here, I'm skipping the details for the sake of time. Please have a read here. But what we are basically doing on high level is we are actually clustering the messages by first transferring these messages into numeric vectors. And this gives us a possibility to do clustering on multi-dimensions. And then for those two dimensions where we have the largest variance, we are actually plotting this, and this helps us to visually find outliers. So we can see that the main cluster seems to be around here. And if we are actually now saying that we are excluding the main cluster, which is in this square from +5 on the x-axis and -5 on the y-axis, so we are excluding this upper part here, then we get all the remaining messages which seem to be outliers. So this is one approach, and it gives us here some messages that stand out of the rest, and we can again plot these messages, when have they arrived over time. And we can also plot yet another neighborhood graph for that. In this case, we see that those messages are outliers, but they are not of a very high syslog priority. And we can also again plot a tag label here. And the second thing, coming to the end here, the second thing is an outlier detection based on so-called auto-encoders. So what we are doing here is basically we are using a deep learning approach where we don't have any reference set up front. So we don't actually know upfront if there are any messages that are specifically outliers or not, but we are just using unsupervised learning. And this auto-encoder is basically trying to reproduce the messages based on previous messages. And the worse this is working, the more this actually shows that this seems to be an outlier because it cannot be automatically recreated. So this is the short summary. Sorry for that scientific part here, but please read more details in that very comprehensive tutorial that is linked here, where you also get some Python code on this. And just showing the results here, we are again getting some outlying messages. We can plot those messages over time, and we can also again look at the neighbor graph and the cloud. So summing up, what I have showed you is that you can easily, with this notebook, first of all, you can get it if you want it. So please reach out to us, and we'll be happy to give it to you so that you can try it in your setup. And once you have it, you can easily connect to your server using the REST API, get the log messages for a certain time frame, and then you can do some text-based analysis, showing word clouds, showing different sorts of charts depending on what you like most and what you need most. You can put topology information in addition, so that you can put this in relation to the actual topology setup. That's what we showed here. And you can also put tag information. And for the final part, if you want to look deeper into this, you can also play around with log anomaly detection. Thank you very much for listening, and have a nice day.